We have seen Laplace transform of elementary functions in the last video. In this video we will see how to what are the properties of these Laplace transforms. Some very few of its properties we will derive, as in the case we have done for Fourier transform, and then before we move on, before we apply these techniques, these properties and Laplace transform to applications. Okay, before you apply to differential equations and solve them, we will just derive some properties of this Laplace transform in this video. We can also do some other some more complicated functions. We can calculate Laplace transform, but let's refrain from doing that because it's as and when it is required, we can do we can find the Laplace transform of certain functions, other than these elementary functions what we have done so far. So let me start with the properties. First property is properties of Laplace transform. So to start with this kind of shifting property, if you have if f bar of s is the Laplace transform, which is the Laplace transform of f of t, which is function of s, then Laplace transform of e power minus a t times f of t is actually equal to for a Laplace transform of at s plus a, where a is a real, number. So we can easily see this one. If f bar is actually representing the Laplace transform of f, which is assumed to be exponential function of some order, then we will see what is its product with exponential function e power minus a t f of t, for which if you take the Laplace transform, and then it is a function of s. So by definition we can write 0 to infinity e power minus a t f of t e power minus s t dt. So you can combine these two to write 0 to infinity e power minus t times s plus a into f of t dt. So this is clearly the Laplace transform of f at s plus a. So this is as simple as this. If a is not real complex, then you may have to worry. So even otherwise it should not be a problem, because e power minus st. So if a is a real constant, then this is the case. If a is a complex number, for example, if it is like this, a is a complex number, and then s, we know that s is greater than a, s is greater than some suppose if you look at this function e power minus a t times f of t, which is exponential of order, some order. So s is greater than beyond that number. So let us say is exponential of order, let us say this is minus a. So you have, if you call this c minus a, let us say if this is the order, s is greater than c minus a. So this is the numbers, s is greater than, so real part of s has to be so s is complex number such that real part of s is greater than c minus a. C minus a if it is a complex number. So if it's a, if a is also complex number, so you can see that real part of c minus a, you can put it this way, and then so s is, so you can think of s is greater than c minus a, so that only real part of s, so that real part of s is bigger than that. Okay, so it's still possible if it is complex, but anyway, so if it is a real, this is you can easily see. So if a is real, this is simply a c minus a, so real part of s, so that is greater than c minus a. So this is clear as a property 1. So what it says is, if you multiply your function, some function with exponential function with minus a t, so if it Laplace transform of it, if you know the Laplace transform of f, that is product is simply Laplace transform with S is translated to S plus A. So, this is one property through which you can give some examples. So, for example, what is the Laplace transform of? I can represent Laplace transform like this R bar. So, you have t power n e power minus a t. So, t power n you know what is its Laplace transform. Laplace transform of t power n is, since Laplace transform of t power n is n factorial divided by s power n plus 1. So, because of this, the Laplace transform this by this property, you have n factorial divided by s plus a power n plus 1. Okay. So, this is one example where you can use, and the second example. So, we have already seen many elementary examples for which you have Laplace transforms. So, you can write for example, e power minus a t sine or cos b t, for example. In this case, for sine, because we know that this is b divided by s square plus b square. Because of this exponential multiplication, we have to replace s by s plus a. So, I will write s plus a whole square. Similarly, Laplace transform of e power minus a t cos b t. Cos b t, if you calculate, that is s divided by s square plus b square, that is with cosine, without this exponential, this is the Laplace transform. So, if I multiply this with e power minus a t, so you have to replace s by s plus a. So, you have s by s plus a whole square by the property. So, this is how you can elementary functions, if you multiply with the exponential functions, you can easily, without calculating its interval. So, you can directly write replacing s by s plus some constant, whatever exponential order which you multiplied. Second property that we use, another shifting property here. If Laplace transform of f of t, which is function of s, is f bar of s, then Laplace transform of f of t minus a times, I multiply with Heaviside function with t minus a. This is actually equal to e power minus a s Laplace transform of f. So, this is what you have. So, this is also you can easily prove. You start with the left hand side, Laplace transform of f of t minus a times Heaviside function of t minus a as a function of s. This should be by definition 0 to infinity f of t minus a h of t minus a times e power minus s t dt. This is the definition. So, because h is 1, if t is greater than t minus a is positive. So, that is t is a to infinity, this is 1. So, you have f of t minus a times e power minus s t dt. So, put this t minus a as a new variable, so we call this x. So, you have dt equal to dx. So, that your, when you put t equal to a, x is 0, when you put t equal to infinity, x is infinity, f of x e power minus s t is a plus x, a plus x. So, a plus x. So, this s a comes out and you have dt is dx. So, this is nothing but e power minus s a times f bar of s. X is the simply number. This is exactly what we need. If we using this, we can easily see, for example, if f of simple example you can take, if it is a constant function, what is this one? So, you can see that Laplace transform of Heaviside function is simply if f of t is 1, f bar of s is 1 by s, we know, and then the e power minus s a, e power minus s a, because we know that f of a Laplace transform is 1 by s. So, this is what you can see. Laplace transform of Heaviside function is this one. Okay. If a is 0 and you have this 1 by s is the Laplace transform of Heaviside function, which is anyway 1. Okay. Heaviside function does not make any sense if you take from 0 to infinity it is 1, and if it is 0 it is 1 here, because it is a constant function. We are only looking at positive side if you are applying Laplace transform. A positive side is just a constant function, you do not say anything. So, Laplace transform, translated version of Laplace transform, that is 0 here, it is 1 here and 0 here. So, little bit this positive between 0 to some a, if it is 0 and then if it is 1 here, that makes sense. So, the translated version of this Laplace Heaviside function, Laplace transform is multiply with the exponential function e power minus sa. Okay. Another example which you can do is if f of t is this, let us say 1 if between t less than 1, minus 1 if it's t is less than 2, 1 between 1 and 2, 0 if t is greater than 2, for example. So, what you have is the function f, which is 0 to 1 it is 1 and it is minus 1, and again so everywhere else it is 0. So, you have this is what is you have between 1 2 this is minus 1, between 0 to 1 it is 1. Okay. So, this is what you have. So, if this is the case, what is the Laplace transform of what is the Laplace transform of f of t, which is a function of s? I can write this function as an application of this property. We can write this function f is as Heaviside function. So, this is for example 1, you can write how we can represent this f of t as 1 minus 2 times h of t minus 1, and then we make it plus 2 times h of t minus 2. So, if you have a wave function, repeated wave function, for example like this 0 to 1, and this again if it repeats like this, you go on adding and subtracting. For example, if I have this and this, I may have to add minus 2 times h of t minus 3 plus 2 times h of t minus 4 plus 0 and so on. If you have as many as you want, as a periodic function if you have, we can represent like this, because we have only these two. So, you can easily verify this one. If t is between 0 to 1, what happens? T is between 0 to 1, if t is between t minus 1 is negative, that is 0, this will be 0, and this will be between 0 to 1, this is going to be between t is between 0 to 1, this is also negative, this is 0, so it is 1. So, both are 0 here, so it is 1. So, this is clear. Between t is between so we can easily see f of t is, which is 1 if t is between 0 to 1. If t is between 1 to 2, what happens here? So, this is 1 minus 2 times h of t minus 1 when you have t is between 0 to 2, that is between 0 to 1, that is 1. So, minus 2, and this will be 0, because 0 to minus 1. So, this is 0. So, you have minus 1 here, and between greater than 2, 1 minus 2 between 2 greater than 1. So, this is always 1 minus 2, and then this plus this is also 2. So, if it is greater than 1, if it's t is greater than 2, what happens? This is 1 minus 2 times t is greater than 1, 2 minus 1. So, this is always 1 beyond 1. So, that is minus 2 plus here 0 to positive side, this is also 2. So, this is also 1. So, you have cancel, this is 1. So, this is actually 1. If t greater than 2, this is 1. This kind of representation is actually 1 here. Okay. If such a function if you choose, what is the Laplace transform of this? Is actually you can represent like this, that function what you have is both are same, these two are the same. So, you can write 1 minus 2 h of t minus 1 plus 2 times h of t minus 2 as a function of s. So, because it is a linear operator, this integral. So, you can split this into, this is your function 3 terms. So, you can write as 3 integrals. Each integral will represent a Laplace transform of 1, that is, this is Laplace transform of 1 as a function of s minus 2 times Laplace transform of h of t minus 1 as a function of s plus 2 times Laplace transform of h of t minus 2 as a function of s. So, you can write 1 by s if it is a constant function, and minus 2 times h of t minus 1. Now, we can use this property e power minus s a. So, you have e power minus s a is 1, a is 1. So, you have by s plus 2 times here e power minus 2 s divided by s. So, this is exactly what we have as f bar of s, if f is given like this. Okay. So, what you have is, it is not 0 here, what you have is it is completely 1 here, such a thing. Okay. That is your f of t. But instead of this, if you have, again if it repeats like a wave, you may have to keep on adding it, you may have to add and so on like this alternatively. Okay. So, minus, first minus and then plus and so on you will get. So, you keep on adding with terms t minus 3, t minus 4 and so on, h of t minus 3, h of t minus 4, the multiplication factor 2, which you add subtract as an infinite series that represents this wave function, periodic wave function that you can see. So, we will move on to another property. These are the examples for this property that what we have seen, this shift property. So, next we will look at the other property of this Laplace transform, that is a scaling property. This is simple. So, if Laplace transform of f of t is f bar of s, then Laplace transform of this as a function of s is this, then Laplace transform of f of a t, this function, the scaled function, is actually what you get is 1 by modulus of a times f bar of s by a, provided a is non-zero, because you are dividing with a. So, such a how do we prove this one? This is the left hand side, Laplace transform of f of a t, which is by definition f of a t e power minus s t dt. Just use a t as a new variable. So, you get a t equal to x, for example. So, you get a dt equal to dx, dt I can write dx by a. So, 1 by a comes out. When you put t is 0, x is 0, when you put t equal to infinity, if a is positive, only if a is positive, this is going to be infinity. If a is negative, for example, if a is negative, and this becomes minus infinity, right. So, for example, a is negative, okay. If a is negative, a equal to minus 1, for example. So, you have a minus here, minus in any case, both the cases, first do with positive case if a is positive. Okay. Let us do with positive cases. If a is positive, this is the case. And what happens, f of x, a t is x, and e power minus s times t is, I replace with t as x by a. So, I write s by a. So, this is equal to 1 by a f bar of s by a. So, this is what you have here if a is positive. So, a is negative case, we have to see similarly. If a is negative, then this integral, this is equal to let me write a t as x, a dt as dx. Okay. So, the same if a is negative, this is the case if a is negative. Okay. So, what happens, 1 by a into dx as your dt, and this is from 0 to minus infinity, because if a is negative and you put t equal to 0, this is 0, x is 0, and if a is negative, t at infinity, this has to be minus infinity, f of x e power minus s by a x. This is what you have. So, again you use minus x. If you use minus x as t variable, one more time, if you do minus dx as dt, so 1 by a. So, if you put 0, x equal to 0, t is 0, x equal to minus infinity, this is plus infinity, f of x is minus t now, and then e power minus x is t. So, s t by a, dt is dx minus dx. So, you have dt. This is what you have. So, you have, if a is negative, minus a is modulus of a, and this is t is a small issue here. A is negative case, if a is negative case, e power s by a minus s by a dx, 0 to infinity, that is also clear. And then a dx is a dt is dx, a is negative, dt is this is fine. So, you have s by a x, dx is dt by a, dx by a. So, this is clear. This is what you have. So, yeah, so you can easily see now. So, you can write this as 1 by minus a, minus 1 by a as minus mod a, if a is negative, this is 0 to infinity, f of minus t times e power minus s minus t by a into dt. F bar of s by a. So, let us keep this as a minus 1 here. So, d of minus t is a dummy variable. So, if you view this like this, so this is actually 1 by a times Laplace transform of this, basically f bar of s by a, even if a is negative. Okay. Where is this? I missed some negative sign. If a is negative, f of a t 1 by a e power minus s by a x, if a is negative, minus here. So, we will look into this as a special case later on. I am not getting exactly the same form. So, we will see if a is positive, this is the case. We will stop here. So, if a is a negative case, we will see later. So, using this, so let us choose this as a positive. Okay. So, if it is a positive, A positive. So, let me choose this way. Okay. So, this is what is clear. So, using this we can do some examples such as, if you take like earlier you have this wave function 0 to infinity, you have a square wave function repeated like this and so on. Okay. If you have like that, so your f of t is that h of t minus 2 times h of t minus, so suppose this is a with A is a wave period. So, every time this is A, every time this is A. So, A plus 2A, 3A and so on, 4A. So, these are the values, it goes every time you are adding. So, let me write it as t minus A plus 2 times Heaviside function with t minus 2A. Again now repeats with this, you can easily see that this represents this one and this one. So, if you add 2 more, it will represent this one. So, you will add 2 more. So, for example, h of t minus 3A plus 2 times h of t minus 4A and so on. You go on get it. So, you will go on getting this as a series. Series represents this wave function, periodic wave function from t positive side. So, what happens to this Fourier transform of Laplace transform of this is, actually you can see if you actually see this one f of t, and you have this series here, some series f of t into e power minus st dt. Because of this e power x minus st, which is exponential function, exponentially decaying function, this series, if you put it, when you put together this function, you can put it into the series f of t, and that series is uniformly convergent. So, you can take this integral inside, and in that sense you can do term by term integration. So, if you do that, you can easily see that the Laplace transform of h of t, that is 1 by s, that is the first one. Next is 2 times e power h Laplace transform of t minus a, that is e power minus as divided by s. Again 2 times e power minus of this is 2as divided by s, and next one is minus 2 times e power minus 3as divided by s and so on. So, what this represent is 1 by s comes out, you have 1 minus 2 e power minus as if you take common. So, you end up getting 1 here minus this one e power minus as plus e power minus 2as and so on. You will be getting this series inside. So, you get 1 by s times 1 minus 2 times e power minus as. This series is less than 1, e power minus a is always if you write like this, e power minus 2as 1 over 1 plus e power minus as, e power 1 over 1 plus e power minus as is this series, okay, because modulus of e power minus as, you can assume that this is less than 1 as a geometric progress series. For sufficiently big s, you can always choose s you have in your control. When you are given function f, s you can choose in such a way that s is bigger than this function exponential order, and s is you can always choose somewhere big, so that this quantity is less than 1. So, you have this series is actually geometric progress series. So, that is this. So, if you actually simplify, this will become 1 by s times 1 plus e power minus as, 1 plus e power minus 2as, that is going to be 1 minus e power minus as. So, this is nothing but 1 by s times, you can represent this as e power minus as by 2 plus as by 2, or rather plus a by 2 minus minus, and so that here also you can write as by 2 plus as by 2. So, this together this is same as the earlier one. So, let me write separately, this is 1 by, this is what you have earlier. So, what you do is 1 by s times you take e power minus AS by 2 out here. So, you get e power plus a, this is to get 1 you have to add AS by 2, and here because you have taken this out another half that remains AS by 2 divide by, again here also you do the same technique, AS by 2 if you take. So, you have AS by 2 here plus here you have minus AS by 2. So, this gets cancelled, what you have is 1 by S times 1 by S times, this is nothing but tan hyperbolic SA by 2. So, this is exactly your Laplace transform of this function, such a function. This periodic wave function which repeats. So, that is what is the Laplace transform you can calculate easily. So, you can easily see that this example what we used this scaling, actually we have not used the scaling here, right. We have not used it. This is one scaling property we have not used. So, this is scaling property, this is not an example for scaling property. So, this is the general example, so example of periodic function, okay. Fourier transform, example of periodic function. This is not actually application of this property. So, anyway, so you have these are the functions, we do not need to scale here. So, directly if you calculate, so you end up getting this one. So, in general if f is a periodic function, another example is general periodic function if you take. If you know that f of t is a periodic function, with period, let us say a, then such is this one, okay. So, this is a periodic function with period a, it repeats, right. It is actually this is actually repeating at is a periodic function of period 2a here, okay, and that is not a. So, here we choose this periodic function with period a, and if Laplace transform of f exists, then what is the Laplace transform of f of t when it exists, is Laplace transform of f of t, which is equal to 1 minus e power minus as, for which you take the inverse. So, 1 over this, 1 over 1 minus e power minus as times f. So, you have this integral 0 to a which you with your period, and e power minus st f of t dt. So, this you can easily see directly by calculating what is the Laplace transform. So, what is given solution for this is if f of t is a function with period a. So, this is f of t plus a for every t positive, this is the case, and assume that a is positive. So, a is also positive with period a. So, what happens if you calculate the Laplace transform of f of t as a function of s, which is f bar of s as 0 to infinity f of t e power minus st dt by definition, if it exists as an integral. What you do is you write this as between 0 to a f of t e power minus st dt plus a to infinity. I split this into two integrals. So, what you do here is I try to put this as t plus a as x, okay, or t minus a equal to x. If I use this change of variable in this integral, okay. So, what you get is dt is dx. So, you have this as it is f of t e power minus s t dt plus this integral f of t is a plus x, x plus a, f of x plus a is nothing but f of x because of periodicity. So, this times e power minus s t is x plus a times dt is dx. When you put t equal to a, x equal to 0 and t equal to infinity, this is infinity. So, you end up getting 0 to a f of t e power minus s t times dt plus here e power minus s a comes out. This integral is f of x plus a is f of x e power minus s x dx. This is nothing but for a Laplace transform of f. So, this is f bar of s, this is also f bar of s. So, if you combine this, is the result f bar of s is 1 over 1 minus e power minus s a times this integral f of t times e power minus s t dt. So, if you know that is a priori it is a periodic function, you can simply, if you evaluate this integral, that is enough to get your Laplace transform. Okay. That is what this technique you can apply here, rather here also you can use in this example where you choose this series infinite thing, you have this series. This is a periodic function with period 2a. So, if you use this periodic function 2a, so you end up getting this one. You can directly calculate from this integral, from this formula also you can get the same result. Okay. So, this property for a periodic function, what is its Laplace transform, that we can call this as property number 4. Okay. So, 4 is this property. If you have a periodic function, Laplace transform of it is given like this, and for which you have seen this example, and property 3 is this. I am rounding up whichever is the property, examples without rounding up. So, second is this property, and the first one is, these are the examples, and this is our first property. So, we will see one by one, and if you see look at the property 3, that is if f is if f bar of s is the Laplace transform of f of t, and this is what we have seen if a is positive. If a is negative, you can work out similarly and see that you will see the same thing. So, this is actually valid for any a positive. So, for any a real number. So, let me say this, whatever may be a, so it just doesn't matter. So, this is actually true. So, we will see that 1 by a. So, this property is true for every a belongs to real numbers. So, that is property 3, and you have seen periodic function. If you have what is its Laplace transform, that is by this formula as this is. So, if you work out if you apply that formula to this function with the period 2a, so you can come to the same conclusion, that is this. So, you can verify that we can give as an exercise. So, directly you calculate it as a series, and you use the property of linear property of this Laplace transform, that is obvious property that we used, and this series converging uniformly. So, you have this integral, you can do term by term integration. So, I have not shown why this is uniformly convergent. This integral Laplace transform, when it exists, it is uniformly convergent for some from s greater than some number, some real number. Real part of s is bigger than, let us say, some a, where a is order of exponentiality of the function f of t. If that is the case, you can once this is uniformly convergent, if this series is also kind of such thing. If you have a series like this, and you can do the term by term, this is a kind of series you have. If this series you can see that is uniformly convergent, you can see that this is actually true because it is a periodic function with period 2a. So, between 0 to 2a is actually finite thing, this is valid, and this is a continuous function on a finite this is on an interval, this is a bounded. So, that is actually this uniformly convergent, that is what you can easily see. So, because of that is uniformly convergent series. So, if you integrate, so you can take this integral inside, that is why that is the property we have used, and see that this is your transformation. So, this is a Laplace transform of such series, such uniformly convergent series. And instead, if you see that function, given function which is a series, which is a periodic function of period 2a, and you apply this formula. So, you end up getting, you calculate only this integral, you will see that you will get the same result. Okay. So, and we can also see some property, that is property of the Laplace transform, that is Laplace transform is uniformly convergent. So, let me do that. So, we use this in the derivatives differentiation, we use this this property, that is let me call this some, this is the property number 4. So, let me call it 5. This property 5 is if f is if f bar of s is the Laplace transform of f of t as a function of s, then rather let me put it. So, if f of t is exponential function of order e power a t as t goes to infinity, then the Laplace integral, that is a Laplace transform, then this integral e power minus s t or f of t times e power minus s t is uniformly convergent. Uniformly convergent with respect to s for s is greater than or equal to or rather s greater than a. Okay. So, this you can easily, this is a kind of form. So, you might have seen a series, n is from 0 to infinity, some f n of x, this is a series of functions. If this is converging uniformly, means as a function of this is, you can see that this is after integration, this is a function of s. So, you can see that this is a sum, this is also kind of sum, and you see that this is uniformly convergent, means is a function of x. So, this can be made less than this converges to or rather if you put some k, this converges to the series, n is from 0 to infinity f n of x as k goes to infinity. Okay. Okay. So, what does it mean? So, this means this minus this can be made less than epsilon whenever n is bigger than some big number. Okay. So, that is what it means, rather k is this is n is this. So, k is bigger than some big number n, let us call this. Okay. This is actually k, n is actually depending on both epsilon and this also function value x, this value set x. So, if I can find such a n's for every x value that is valid wherever x belongs to, let us say some domain D. Okay. So, for every x, if I can find such a big maximum some n epsilon for each x, if you have a maximum value of n epsilon of n of this n existing big number epsilon of x belongs to D. If this is your big number, okay, then this n, if such a maximum exists or the supremum exists, supremum is something which need not be exact. If it is a finite, you call this, let us call this maximum if you do not follow. So, or something bigger than all these numbers. Okay, if it exists, such a number that works for every x in D. So, that is the meaning of uniform convergence. Then you say that this series is converging as k goes to infinity, converges uniformly. So, the same way you can see this one also. So, the same argument holds good. Once this is uniformly convergent, this series, you can do term by term differentiation and term by term integration. So we see the same thing as a function of s, if it is bounded with some other integral which is independent of this function, independent of this variable s, then you say that is uniformly convergent. So this is simple to prove. Proof, let me give you. Since f is of this order and you see that f of t times e power minus st, this one, this if you estimate, this will be less than, because f of t is k times some constant times e power at as t goes to infinity, then you have e power minus st, this is the modulus. So this is less than or equal to k times e power minus t times this is going to be s minus a, is all positive. Now if s is bigger than a, so you choose some a1, let a1 is bigger than a, then mode of f of t times the above, this is less than or equal to k times e power minus t times a1 minus a. Okay. So this is true. Where is this valid? S is bigger than or equal to a1. For every s, if you take s is for every s bigger than or equal to a1, this is always, this quantity is always bigger than that. So this is always bigger than or equal to k times e power minus t times a1 minus a, if a1 is less than s or equal to s, okay, because of equality. So that is what I have chosen. So if I choose a1 bigger than a, then you can write this quantity is because s is bigger than a, and you can write like this. So this is instead of writing this, you can just use this one. If s is bigger than or equal to a1, okay, so where a1 with a1 is bigger than a, let us say. So such a thing, this is always true. So that means left hand side is independent of is depending on s, this is independent of s. So you can take the integration of f of t e power minus st 0 to infinity, this is less than or equal to, so this is uniformly convergent. So this exists, okay. This is because this integration will be the less than or equal to 0 to infinity modulus of f of t times e power minus st dt. This is less than or equal to k times integral 0 to infinity e power minus t times a1 minus a dt. This is actually finite. This is true because this is true for every s bigger than or equal to a1 which is bigger than a. That is the meaning. Okay. So this is the meaning of uniformly convergent function of s, independent of s, beyond some s bigger than a, you have uniform convergence. So because of this, I can take f bar of s which is integral 0 to infinity e power minus st into f of t dt. This is uniformly convergent integral. So I can differentiate with respect to s, so that I can take this derivative inside this integral, just like how I take, if it is uniformly convergent series is a function of x and is from 1 to infinity, let us say 0 to infinity, I can differentiate this whole thing as I can take this derivative inside, this is same as n is from 0 to infinity f n dash of x. So same thing, so this is same as integral 0 to infinity d ds of the integrand e power minus st f of t dt. Okay. This is true only if this is true. So this is uniformly convergent. Because this is uniformly convergent, we can prove that this is true, and you can also do the integration of f bar of s ds. Let us say some wherever s is the domain s, if s is bigger than a, so you can think of s to wherever s is s to infinity. S to infinity you can integrate as this function and this is integration of s to infinity ds of this integral 0 to infinity f of t e power minus s t dt. So, this is again I can take this integral inside this integral. Okay. So, that is same as 0 to infinity integral s to infinity e power minus s t ds f of t dt. So, these are same, both are same only when it is because that integral is uniformly convergent. So, this is the property, important property, so which is analogous to what we had in series, functional series, function series. That is where if you talk of this notion called uniformly convergence. Because of this you can do term by term differentiation, term by term integration in the series. The same thing is you can do for if it is an integral. So, summation is also the integration is after all is a summation, limit of a summation. That is what that is the reason we can do these two results based on that. So, one can show that. Okay. So, you take this as a property and then we can do a differentiation of Laplace transforms. So, we will look at the Laplace transform of its derivative. So, if I have so far we have seen certain properties of Laplace transform, that is to start with what is the scaling property, shifting properties, start with the shifting properties and then one or two are the first two shifting properties and then we had a scaling property and then what is the Laplace transform of the periodic function, how do you get what is the formula for that, there is as another property. And also you have seen this Laplace transform is if this Laplace transform is uniformly convergent integral which is independent, that means it is a finite for all. So, it is bounded with some number, some integral that is independent of s. So, that is kind of a uniform convergence. So, that you can do term by term differentiation, term by term integration of this integral. So, that means you can derivative you can take it inside this integral or integration, when you do the integration of this Laplace transform you can take that integral inside the other integral, okay, inside the integral of the Laplace transform. So, these are the properties we had so far. So, we will look at derivatives and other properties of this Laplace transform in the next video. Thank you very much.